So this is kind of a miscellaneous handout with some ideas to consider. So let's see what's going on here. So here's the topic, basically, factorial experiments in a randomized block design. So you look at the model here at the bottom of the page. It looks fairly straightforward. Y, I, J, K is that expression there. Main effect for factor A, main effect for factor B, interaction between factors A and B, and an error term. So a pretty standard kind of a model that we've looked at before. So now the idea is that suppose the complete experiment is replicated several times. RK represents the blocks or replications. The randomized block model then looks like this. So now we picked up an extra term in the model for replication, and then the tau ij is the same as we had before. So putting it all together into one equation, we look at something like this. So there's a term for a replication, term for A, term for B, an interaction between A and B, an error term, and there's no interactions between the R and A or B. We leave those off. So here's a small example that begins here. So things might look like this. We might have A has, what does it say here? 3 levels, B has 2 levels. So we have A1, B, these are all scrambled in order. So A1 with B1, there it is. And then we have A2 with B1, A2 with B2, then we have A3 with B1, A3 with B2. So there's the 6 cases in a scrambled order because, as it says here, that's been randomized. So we've randomized the order in which those are run. So that's replication 1. Now if the experiment is repeated a second time, we get the second row here. Same 6 combinations, but again in a random order. And then a third replication and a fourth replication. So we have something that looks like this. Now we have the start of an ANOVA table here. Replications, since there are 4 replications, we get 3 degrees of freedom. Treatments is the combination of both A and B, and there's 6 combinations giving us 5 degrees of freedom on that, and it breaks down into A, B, and AB with 2, 1, and 2 degrees of freedom. And since overall there's 24 observations, we get 23 degrees of freedom for total, and subtracting out, we have 15 degrees of freedom left for error. This table at the top is kind of big and a little hard to go through here in class, item by item. But you've seen this kind of a thing before. You remember this handout from last time, which I called EMS rules. So there were some steps to go through in filling out this kind of a table. And when we finally get down to the end, we can figure out a column of expected mean squares for the various effects in our model. So that's what I'm leaning on here. And I'm just going to basically say, you'll have to look at this yourself and check that it works. There's a lot of items in here to check out. So anyway, the problem with this layout is that it has all these interactions between R and the other factors, like that one, R with A, R with B, R with AB. And I don't really want those in my model, so we take them out. And so here in the second table, he calls it a reduced model, and we've got a row for R, A, B, AB, and then error. Now for R, we get its expected mean square from there. For A, we get its expected mean square from there. But we dropped the sigma squared RA because I don't want that in my model. So take that away, and I'm left with sigma squared E plus 8 phi A, which is what we see here. And for B, let's see, I'm here, and I don't want this sigma RB because I'm taking that out of our model. So what's left is the expected mean square for B. And finally for AB, I'm right here. And I take out the RAB because I don't want that term in my model. And so I'm left with that, which you see here. So I'm not sure what our source here is telling us exactly. It started off with the this big layout with all these RA and RB and RAB terms in it, which we don't really want in there because those we're going to take out of the model. So they really don't belong there. So I'm not sure why this is there. But anyway, this is the one that we're trying to look for finally to get our expected mean squares. Remember earlier in this handout, there was here. this model here is what we're trying to fit for the data. So we have R, but no RA, no RB, no RAB, just those terms are in our model. So once we get over here, this what's it called, table 8.3. Here, looking at the expected mean square column, we can see that for the F tests, we have mean square error as the denominator for F tests. We're going to test for R, mean square error is the right denominator. If we're going to test for A, B, or AB, again, mean square error is the right denominator. So that came out pretty simple anyway in this particular example. All right, so we begin another example here on the bottom of the page. And if you look at the next page, I think visualizing the data tells us what's going on. So somehow we have 5 operators. We have nozzles, ABC, 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 etc. And then we have replication 1, 2, and 3. So here's the model we want. We put an RK for the replication, an NI for the nozzle, an OJ for the operator, and then an NO interaction is also in the model, and then there's an error term. So those are the terms that I want in the model. Now, the RK levels are random, as is usually the case. The replications are random. Here so we'll make that assumption. The OJ levels are also random. The operators are just a random sample from a pool of available operators, and so O is a random factor. The N levels are fixed. The nodules are a fixed effect. Okay. So we start our method again for finding the expected mean squares. And so again, as it requires, we put the terms that are in the model over here, like that. And then we start filling in the top. The indices are I, J, K, and M. And M is kind of a dummy index here. Now I goes with NI, so that one's fixed. J goes with O, which is random. So I label that. K goes with replication, which is random. So that's filled in there. And finally, M is just the error term, and that's always random as well. So we fill in that much, and then we fill in the numbers 3 levels for I, 5 levels for J, 3 levels for K, and then for the error we kind of just vacuously put a 1. So anyway, we fill in those things on the top, and then we start the method for filling in all these numbers down here, and finally multiplying things together, come up with this expected mean square column. So again, I'm going to turn that on your shoulders to look at these numbers here and see that you can reproduce them yourself by following the method. If you have any troubles with that, ask me, and we'll go through this with some care. But for the moment, I won't say anything more about here in class. So we look at this expected mean square column that we have here, and let's see what denominators we might specify. Let's see, it's probably on the next page as well. So if I want to test about R, the proper denominator would be mean square error. If I wanted to test about N, the proper denominator would be this one here, the NO interaction. If I wanted to test about O, the proper denominator would be again error. And if I wanted to test the NO interaction, the proper denominator would again be the error mean square. So anyway, by looking at these expected mean squares, we can figure out the proper F ratios for testing the hypotheses. And that's the purpose of having this layout, to enable us to do that. Then here's the Minitab output running this data. It gives us R is random, N is fixed, O is random, which we had to enter into the program. And here's the ANOVA table, and here's the layout for the expected mean squares over here, and we can see what the proper ratios are. So let's see, starting at the bottom for the NO interaction, the proper denominator would be 5, that's the error. So looking at these mean squares, the proper denominator for this one is this one. And so 96 going into there is approximately 2.35, so that's where that F is coming from. Now if I want to test the next one, O, let's see, that's a third one here. I'm using my level here. I want to test for O. That's the third one up, which is the second one here, which is the third one here. So the right denominator is again 5, the error. So the test O, the proper denominator should be the error. So let's see. There's O, there's the mean square for O, there's the mean square error. I combine that, and I get about 2, so that's about right. So again, we can check that the program is doing what we think it should be doing from the expected mean square column. Now when we come to the next one, something different happens. When we come to N, is right here. Under the hypothesis, this is 0. So what's left is that, and I estimated this here, which is the NO interaction. So the proper denominator for which one am I talking about? For N is the NO interaction. So for N, that's the second line upper denominator is the NO interaction, which is here. So 700 divided by 200 and something like that is where the 3 comes from for the F statistic. And there's one more to check out. But anyway, that's all I'm indicating to you is that you can do some hand calculations and check that the program is doing the right F ratios, which you hope it is, because we'd be really in trouble if the program was somehow giving us the wrong F ratios. Here's a plot of the means. Good idea to do that. Now, as this handout continues, it says, here's the Minitab output for the model which has replication interactions. So what they're going to do is take the same data, but they're going to change the model. They're going to put in all of these terms here in the model. So there's going to be an R, which we had before. They're going to add in an R in interaction. They're going to add in an R O interaction. And well, there's more that's possible, but that's all they've added in here. So that's what you can see in comparison to the previous model. They've got, in terms of the previous model, here, they've added in R, N, R, O. So they've added in if they call it some replication interaction into the model. So now they've got to go ahead and redo everything all over again as far as the analysis and as far as the expected mean squares. Now here's the Minitab results for the expected mean squares. And so we can take a look at this and see that everything has a proper denominator except, let's see, which one? It says here, there's no direct test on nozzle. Let's see, that's N. So there's N. There's the expected mean square. And when we look at that expected mean square, and then we look at the other options that we have, we would say there isn't anything else in the list whose expected value is what's in here, excepting the N term there on the side. So there's no natural denominator for that F ratio. What they did here in Minitab is just put a little star there to indicate that there's some kind of trouble. And then there's a star up here as well in the list of F's. So it's going to describe down here building a so-called pseudo-F ratio. So looking at the options that we have here, we have expected value of mean square Rn is that. That's from the third line here. Expected value of mean square NO is that, and that's from the NO line here. And then if we take the sum of those two, and then subtract from it the mean square error, You see, the idea here is supposed to be intuitive. We like a denominator for testing about nozzle. We look at its expected mean square, and that's here under the hypothesis. So we don't see anything else in the list which has some of those three pieces as its expectation. So we take what we have. We see a 3 times 6 here. We see a 5 times 3 there, which we see here. And we pull out these two and we say, well, let's add these two mean squares together. So if I do that, I pick up this and I pick up this. But the trouble is I've got this 7 in there twice. So I'm going to balance off by subtracting it off one time. And that's what's being suggested here. So this isn't supposed to be rocket science or anything. We're just looking at the options there. And we're building a mean square. Here it is right here, finally. Mean square Rn plus mean square NO minus mean square error. And the expected value of that, putting in the pieces, is what we want. So we build a mean square, sort of a combination of mean squares that has the right expectation. So in this handout, this constructed mean square is called here in almost the last line, just simply MS. Not called MS anything, just MS. So there it is, mean square Rn, mean square NO minus mean square R. That's going to be our denominator. So here's the numbers. And here's the pseudo F of 3.8. And now we have the issue of, well, how many degrees of freedom does that MS have? And so here we have to come up with a formula that's like this, what's it called, the Satterthwaite formula for estimating degrees of freedom that we encountered way before in talking about the Welch t-test, for example. So this is the corresponding formula we're going to have right here for estimating the appropriate degrees of freedom. And apparently all that arithmetic comes up to be 4.2. And so this particular source says 2 and 4 degrees of freedom, 5% F value of that, or rounding the other way, 2 and 5 degrees of freedom, it's that. Either way, the conclusion that we make is the same. Okay, so what did you see here in looking at all this detail? Basically, we started back on the layout here that we got on a mini-tab, and we noticed that there wasn't a proper denominator for testing n. So how do we handle that? We basically construct a pseudo-F ratio, as was done here. So we went through the work of building the other mean square. We had to estimate its degrees of freedom over here. We got 4.2, rounding it to either 4 or 5. And so we can build a pseudo-F test for testing that particular factor. So that's what's being illustrated here in this source. Okay. Type this out nicely. Basically, this is going to be some proofs of things. So what's the scenario? It begins with what's called there A1. And that's the old result about the distribution of a sample variance. If the x's are independent normals, then n minus 1 s squared over sigma squared which is this kind of a sum, is chi-square m minus 1. So that's a basic result about a distribution where we get a chi-square coming out, the distribution of a sample variance. Now that's going to be used in several places along the way here. Let's see how. So we're going to look at a fixed effects model, Yijk, independent normal mu sigma squares. I goes 1 to A, J goes 1 to B, K goes 1 to M. Then in this fixed effects model, the sum of squares cells, as I called it, is this sum, this double sum here of y bar ij dot minus y bar triple dot squared, and then factor n out in front there. And so this is what I want to talk about. So the next step is just to move the n down into the denominator, and so it reads like this. Now looking at this, let me introduce some new notation. Let's let xij be this y bar ij dot. Now those variables, they're each an average. Those variables are normal mu sigma squared over n. And then the mean of these xij's, the x bar dot dot, would simply be y bar triple dot. So this expression that I'm looking at here, contrasting with A1 at the top of the page, we can say the conclusion. Sum of squares cells over sigma squared is chi-square AB minus 1, AB being the number of terms in the sum. Okay. So what I'm trying to do is to say, how do I show that this kind of thing has a chi-square distribution? So I write it in a certain way, and I say, well, when I visualize what I have here, and I introduce some different symbols just to clear the air a little bit, let xij be that, then x bar double dot is that, and so that's what we have there, and this denominator is the right thing for that. And so all the pieces are lined up in what I'm looking at here. Quote A1 and say, there's our answer. And the number of terms of this sum is A times B. And so we get AB minus 1 for degrees of freedom. So anyway, that's the way we argue that sum of squared cells divided by sigma squared has a chi-square distribution. Then, moving on, sum of squares A over sigma squared. Here's sum of squares A over sigma squared written out. What kind of distribution does this have? Well, it's going to have a chi-square distribution with A minus 1 degrees of freedom, and I said there, by the usual argument. So what I want you to see is just in your mind, to look at this and say, well, let's look at this expression. Let's take this Bn and throw it down into the denominator of the denominator, like I did there. And then what I'm looking at here, let's call that thing xi, and that's x bar. And so what I'm looking at here, I can go back to A1 and just directly claim this kind of thing has got to have a chi-square distribution with A minus 1 degrees of freedom. So that's what I mean here by just simply saying by the usual arguments. This is not supposed to be hard. There's a couple steps in there. Now, looking at sum of squares B over sigma squared, here's the formula for it. It's the same kind of thing as we had for A. And that, by the same kind of argument, can be shown to be chi-square B minus 1. Now, We're still talking about the fixed effects model, and there's an interaction parameter in the model, and there's the sum squares for the interaction. Now this one is hard to work with. We can't sort of easily do an argument like these kind of things to verify directly that somehow this one has a chi-square distribution. So we take a different approach. And here it is. We say, remember our algebra, we didn't prove this, but we said it was true. Sum of squares cells, the sum of squares A, plus sum of squares B, plus sum of squares AB. And what do we know about these four pieces? We know this one is chi-square by what we did in A2 above. We know this one is chi-square. We know this one is chi-square. And this is the one we're shooting for. And all we can say is that it's greater than or equal to 0. Now, with that setup there, we rely on what we call Cochran's theorem. By Cochran's theorem, the last variable in this equation has to be chi-square. So that's an application of Cochran's theorem. Now, I'm trying to recall. I hope I mentioned it. Cochran's theorem was back in the first handout, on the very last page, I think. And this is it. This is where we're using it. So you can go back to that very first handout, the very last page of it, which was page 12, I believe, and see Cochran's theorem expressed there. So what I'm doing here is to rely on Cochran's theorem for the conclusion. Cochran's theorem basically said that if you have chi-square equal to chi-square plus chi-square plus something else, as long as that something else is never negative. Now our expression is here, and you can see it's a sum of something squared, so it could never be negative. It's always greater than or equal to 0. So that's satisfying. So we've got everything all set up to apply Cochran's theorem to say the one piece that's missing, maybe that one, must be chi-square. It's the only possibility for it. And so that's the conclusion that we write here. The degrees of freedom for this last piece has to be such that they add up on both sides of the equation. So take the degrees of freedom you have here, subtract these degrees of freedom, subtract those degrees of freedom, and you're left with the degrees of freedom for the AB that we want. And so there it is, the little algebra that comes out to be A minus 1 times B minus 1. So this is a proof anyway for the fixed effects model for how do we verify that those sums of squares have actually chi-square distributions. This is the argument. Other side, side 2. Let's do the same kind of thing for the random effects model. So here's the random effects model. We've got alpha I normal, beta j normal, alpha beta ij normal, eijk normal. All these random variables are independent. Now our goal here is to show this kind of thing. So basically what we're trying to do is to talk about the distribution of the sum square interaction in the random effects model. Now this stuff here is what we would call the unrestricted random effects model. You remember when we encountered this, we had both restricted and unrestricted models. This is the unrestricted model. We have no assumptions about sums or anything like that in these terms that are in the model. So notice this is an unrestricted model. So in that case, how do we show this as this chi-square distribution? So we begin here, sum of squares AB. So there's the formula for sum of squares AB. And now what I'm going to do is to substitute in what each of these pieces are equal to in terms of the model. So for example, y bar ij dot right there is mu plus alpha I plus beta j plus alpha beta ij plus e bar ij dot. The I and the j are fixed, and I'm only averaging over the third subscript k. So I do that for y bar ij dot, and do the same thing for y bar I dot dot. And get these pieces here, and do the same kind of thing for y bar dot j dot, and get these. And do the same thing finally for y bar triple dot, and get these. And now we look at this mess that we've created here, and we say there's a lot of cancellation going on here that we can take care of. So cancel the things that cancel. For example, you can see here's plus alpha I, there's a minus alpha I. Cancel those off. And there's other cancellations that go on in here as well. And when you've taken care of all that, it still doesn't clean up very well, but you get this kind of expression here. So what I'm going to do is to put the ij terms together there, and call them by a shorter symbol, xij. Then the next piece here is the average of those over j. And then the next piece is the average of those things over I. And finally, the fourth piece is the average of those things over both I and j. And we get that. So anyway, this messy expression that we have here in my shorter notation is xij minus x bar I dot minus x bar dot j plus x bar dot dot. Now these xij's that I have here are again right here, and I look at the distribution of these things, and it's a sum of two normal random variables, which is again normal. The means of the pieces are 0, so the overall mean is 0, and the variance is the sum of the two variances. We have sigma squared AB for the variance of the first piece, and we have sigma squared over n for the variance of the second piece. And so what I want to do is to come right here and say these xij's are distributed like the variables on the other side. We're going to call them A2. Okay. Xij minus that mean, and minus a minus and a plus, the overall mean. So that's the formula that we had before. And what I have in the denominator is the variance of that variable. Sigma squared AB plus sigma squared over n. So that's what I gave in the denominator, the variance of that variable. So looking at this, and what we did on the back side of this page, we can claim by that work, this variable is chi-square a minus 1 times b minus 1. It's just a direct application of the result of the previous page. And then cleaning that up a little bit, going back this way, multiplying 2 by n on top and bottom. Now this top here is really the sum of squares AB. And the denominator is what it is. There it is, there it is. And so that's what comes out. So anyway, we've made this argument with those kind of steps in there, that sum of squares AB, the interaction sum of squares, this is in the random effects model, divided by this constant, has the chi-square distribution with those degrees of freedom. So what do you make of this? This is kind of a messy proof in a way. But what you can see, first of all, is that the answer is different for the random effects model as opposed to the fixed effects model. Different distribution. Then we could say, well, what if we had the restricted model and we tried to construct a proof like this? How would that go? Well, I'm not going to do it, okay, so don't panic about it. But anyway, that would be another whole argument to say, how could we verify a chi-square distribution for the other model? Well, I have a third handout here today. I'm looking at the clock. I don't have time to talk about it, so maybe let's just leave it until after the test. We'll take it up next week. Okay, so that's enough for today.
Test is Thursday then?
Pardon?
The test is Thursday.
The test is Thursday. Come here. This is where it'll be. I'll try to bring in some buckets of pain and sorrow and suffering to share with you for Thursday.